Hello everyone, this is Bsc TY course. It's linear algebra. Yesterday we have discussed how to calculate the orthonormal basis of an inner product space, and then we solved one example. There we considered V be the inner product space of set of all polynomials of degree less than or equal to 2, whose standard basis is 1x square, and using this standard basis we find one orthonormal basis of that inner product space. Now I am going to discuss today one theorem, theorem 4.4.3. Theorem 4.4.3. If V is a finite dimensional inner product space, if V is finite dimensional inner product space, this denotes inner product space, and W is a subspace of V, and W is subspace of V if W is a subspace of V, then V is a direct sum of its a subspace and orthogonal complement of the subspace W. This denotes V is a direct sum of subspace W plus its orthogonal complement. More particularly, V is the direct sum of subspace W and its orthogonal complement. So first understand the statement of this theorem. If V is a finite dimensional inner product space and W is a subspace of it, then V is a direct sum of W and its complement. That is, V is an internal direct sum of subspace W and its complement. Now, in this theorem, we must prove two things. In proof, we have to prove these two things. First is, any element of V can be uniquely written in the sum of this. That is, every element of V is summed like that. W dash, where W belongs to W and W dash belongs to orthogonal complement of W. And the second thing we have to prove is that W intersection W orthogonal complement of W is singleton 0. These two things we have to prove in this theorem. Then automatically the theorem is proved. So if V is a finite dimensional inner product space, so proof given that V is a finite dimensional inner product space, and W is its subspace. Therefore, we can say that W itself is a finite dimensional inner product space. This implies that W is itself is a finite dimensional inner product space of vector space V. Now, if W is a finite dimensional inner product space, then consider dimension of W is equal to R. Then let W1, W2, WR is the orthonormal basis of W. Is the orthonormal basis of W. Hence, if these R elements forms an orthonormal basis of W, then dimension of W is R, which implies that dimension of W is R. Now, consider one element. Consider one element. If small v belongs to capital V is any element, then consider another element V0, which is equal to V minus V W1 inner products of V and W1 and times W1 minus inner product of V1 W2 minus inner product of V WR, and we know that this element is orthogonal to each elements of W1 W2 WR. We know that V0 is orthogonal to each of W1, W2, WR. Therefore, it must go to the orthogonal complement of W, because this is the basis of W. This implies that V0 belongs to orthogonal complement of W. If V0 goes to orthogonal complement of W, then from equation number 1, we can write V is equal to V0 plus V W1 times W1 plus plus V WR times WR. Now, if V0 belongs to W, we prove that V0 belongs to orthogonal complement of W. Now, this inner product goes to field, this inner product goes to field, and W1, W2, WR are the orthonormal basis of the subspace. Then we can directly say that this element belongs to W. So, every element of V can be written in the linear combination of orthogonal complement of W and W. So, we prove first concept of this theorem. Now, second, now we have to prove that the only 0 is the common element in both W and its orthogonal complement. Let V belongs to W intersection W perpendicular. That is, V is the common element of subspace W and its orthogonal complement. This implies that V belongs to W and V belongs to orthogonal complement of W. If V belongs to orthogonal complement of W and V belongs to V, then we can say that this implies that inner product of V comma V is equal to 0. This implies that V is equal to 0. Because we know that only those elements whose inner product with itself is 0 is only 0 element. Therefore, we proved second thing. Hence, we can say that this implies that W intersection orthogonal complement of W is singleton 0. Hence the proof of this theorem. Hence, in this theorem we first prove that every element of V can be written in the linear combination of subspace W and its orthogonal complement. And then we prove that only common element between subspace W and its orthogonal complement is singleton 0 itself. Now one corollary depends on this theorem. W is equal to orthogonal complement of W and its orthogonal complement. We have to prove this. Where W is a subspace of an inner product space V. Now let V belongs to W. V belongs to W. And U belongs to orthogonal complement of W. Then we can directly say that inner product of V comma U is equal to 0. This implies that V belongs to orthogonal complement of W and its orthogonal complement. This implies that V belongs to orthogonal complement of W and W. This implies that W is a subset of orthogonal complement of W and orthogonal complement of W. This is first. Now, we know that W is isomorphic to orthogonal complement of W and its orthogonal. This implies that dimension of W is equal to dimension of orthogonal complement of W and its orthogonal. This implies that W is equal to orthogonal complement of W and W. So this is from 1 and 2 we can say that W is the proof of the corollary. So understand how to prove this. We have to prove that if W is the subspace of an inner product space V, then W is equal to orthogonal complement of W and its orthogonal. So we take any element of W and U belongs to W complement, W orthogonal complement of W. If U belongs to orthogonal complement of W, then U must inner product of U must be 0 with U. So inner product of U must be 0 with V. So we can say that V belongs to orthogonal complement of W and its orthogonal. So if V belongs to W implies V belongs to orthogonal complement of W and its complement, then we can say that a subspace W is a subset of orthogonal complement of W and its orthogonal. So second, and also know that subspace W is isomorphic to orthogonal complement of W to its orthogonal complement. Hence we can say that two vector spaces are isomorphic, then their dimension is same if and only if two vector spaces are isomorphic if and only if their dimensions are same. So we can say that dimension of W is equal to dimension of orthogonal complement of W to its orthogonal complement. So we can directly say that W from 1 and 2, this is hence the proof of this theorem. Now 5.1 extension field. Definition only. Extension field. So write down the definition of extended field, extension field. If first definition, if F is a field, then K is said to be extension field of a field F. Extension field of a field F if K contains F. If K contains F, that is F is a subset of K, then we call K is the extension field of F. Now definition second. K is said to be extension. K is said to be extension field of F. K is said to be extension field of F if K is subfield. If F is subfield of K. F is subfield of K. So this is very important definition, extension field. So when we say that any field is a extension field of some field, if F is a field, then K is said to be extension field of a field F if K contains F. That is, F is a subset of K, and K itself is a field and F is a subset of K. Now for example, if Q is a field, then Q of root 2 is the extension field of Q, because Q is a subset of Q of root 2. Also we can say that R is a subfield of C, therefore C is an extension field of set of real numbers. तर आजचं लेक्चर इथंच थांबूया. तर आपले लिनियर अल्जेब्रामध्ये 2 युनिट संपले. आपण हा कोर्स इथंच थांबूया. नंतरच्या लेक्चरमध्ये मी तुम्हाला कॉम्प्लेक्स अनालिसिस स्टार्ट करणार आहे. खूप इम्पॉर्टंट आहे सेट नेटसाठी. तर आपण नेक्स्ट लेक्चरपासून कॉम्प्लेक्स अनालिसिस सुरू करूया. आपले इथं 2 युनिट संपले, 1 युनिट बाकी आहे, होऊन जाईल ते पण. थँक्यू.